Take a look at some division of radicals. We look at two radicals that are put together, or division basically inside of a radical. We think of it as two radicals that are put together. So we can split it up. This method's really only effective when your denominator is a perfect square, or cube, or fourth root, or whatever root you're working with. The only reason that's useful is because when we're doing this, we can't have a radical end up in our denominator. If it's perfect to begin with, then it's going to be really easy to reduce this to, just numbers and variables and no more radicals. And then, of course, you can simplify the top by taking out the biggest perfect square that goes into whatever your radical happens to be on the top. In this case, 60 breaks to 4 and 15. X to the third is x squared and x. So then you'll get 2x radical 15x over 9y, and you'd look to reduce numbers or variables. Remember, if you had, say, y to the third up here and y to the first, that would give you a y to the second on the top. So keep the exponent rules from way back when in your mind as you're dividing these radicals. Not just looking to reduce numbers, but also the exponents on top of your variables. Sometimes the denominator is not going to be perfect square or cube, such as in our example here, number 5. The strategy you'd want to do for a non-perfect square or cube is to divide first. As you can see, we have 40 and 8. 8 goes into 40, it goes in 5 times, so you just make that a radical 5. And there's nowhere else to go from here. In the sense of ones with, say, variables, we'll look at the cube root of number 7 over here. We can divide our numbers and then subtract our exponents and turn it into one big radical with no fraction anymore. So we'll have the cube root of 432 divided by 6 is going to give us 72. X to the 12th, x to the 5th is x to the 7th. Y to the 6th, y to the 1st is y to the 5th. And from there, you're going to simplify the radical as you would, in the beginning of the unit, just plain old simplify. Biggest perfect cube that goes in is 8. X to the 6th, y to the 3rd. Remember, we're looking for perfect cubes divisible by our index. Our index is 3, so 6 and 3 are divisible by 3. And then a 9x y squared is left over. So we reduce our perfect 2x squared y cubed root 9xy squared. And that's just what you do in 2 of the cases. So the first case is, okay, my denominator is perfect square. Reduce the denominator, reduce the top, simplify. Second case is I don't have a perfect square in my denominator, and I'll divide first. And I'll go as far down as it'll let me go. Now there's some other cases. When you divide your radicals, so you start with a non-perfect square down here, you divide them and you can't simplify it. You have a radical in your denominator. Well, what we need to do is we need to take what we have in our denominator and turn it into a perfect square. So sometimes it's really easy. As you know, you can't multiply a fraction by, or a number really, by anything but itself to keep it the same. So by 1, sorry. So we multiply something by the same thing top and bottom, we're multiplying by 1 to keep it itself. Why did I choose radical 3? Well, because if you square 3, it's going to give you 9, and that will give you a perfect square. On the top, it's going to make another radical, but we don't care, as long as we care about not having radical in the denominator. That's all it is. Square root of 9 is 3. And there's your answer. So if we try that again on number 2, you have a 12. Okay, you could multiply it by radical 12 if you split this up. But I think that there's a perfect square closer to 12 than just multiplying 12 by itself. You could always, with square roots, pull the strategy of multiplying the denominator by itself to get rid of the radical. Think about 36. If we do times radical 3, that will get rid of our denominator. So you do have the ability to choose. Had we multiplied by 12, we probably have to take a perfect square out of the numerator. But either way will work. This ends up being a little different for cube roots, but it's the same idea. We have to multiply the number by 1, right? So something over itself. And in the past, we had to make these into perfect squares in our denominator, right? So radical 3 times radical 3 gave us radical 9, which is a perfect square, gave us 3. Radical 12 times radical 3 gave us radical 36, which is 6, which is a perfect square. In this case, we need perfect cubes. So if you look at problem 2 here, you have a cube root of 9 on the bottom. Well, if you multiply cube root of 9 by cube root of 9, you're going to have a cube root of 81, which is still not a perfect cube. But cube root of 3 will get you where you need to go to. It'll give you 27. 27 is a perfect cube. So now your radical in your denominator is gone. And you simplify at the top if you possibly can. In this case, you can pull an 8 out. So then, we'll pull this up over here. And then, of course, in the end, you can reduce. You will. 12 over 3 is going to give you 4 cube root 6. So the biggest strategy you're trying to do is square root, get a perfect square in your denominator. By multiplying your radical down here by whatever number will produce a perfect square. Cube root, produce a perfect cube in your denominator by multiplying top and bottom by whatever number will create a perfect cube in your denominator. One more case that we'd look at would be, so we have a binomial, if you will, in our denominator with a radical. What we need to do is multiply by the conjugate. Remember, the conjugate is used to get rid of radicals. It's used to get rid of anything that's on the denominator really that we don't want in this case. So we got to multiply top and bottom by our conjugate. Sorry for that. So distribute out the top, distribute out the bottom. So notice this does the same thing as what we were doing with our rationalizing before, creating a perfect square. This not only creates 2 terms on the bottom that will cancel, but a perfect square at the end. And that way we can get rid of any radicals in our denominator. And that's the real purpose of the conjugate. Because the square root of 9 is going to give us 3. And then reduce again if possible. I see a 2 comes out of everything here. Remember, you're only reducing the coefficients. You can't reduce what's under your radical. Those are unlike terms. So there's your final answer. The big goal of rationalizing is to make perfect squares or cubes or whatever root you're working with in your denominator so that you're left with just a number down there.